Hello, everyone. So my name is Ranjit Menon. I'm a network software engineer at Intel. This is Omar Cardona, who's a principal dev lead at Microsoft. And we're here to talk about improving security and flexibility within the Windows network. I was just thinking, we have two back-to-back Windows sessions at the DPDK Summit. How about that? Pretty cool, huh? And, thanks. And the other one was last year at the summit, we actually introduced support for Windows, DPDK on Windows. So we had one session in the entire summit. This year we have two. So next year, we'll do more. Okay. Okay. Is it on? There you go. So this is so just a quick agenda. This is what we're going to cover. I'm not going to read through all of this, but as we go through, you'll see as we talk about it. So this is the story so far. Harini mentioned in a previous presentation what we did. Last year we announced support for DPDK, Windows DPDK at this summit, and then the code is now available in a draft repo. It's not in the mainline repo. We are trying to get it into the mainline repo. There's efforts going on there. We have to clean up the code. We have to make it style, look like nice and all that stuff, but we'll get to all that slowly. At any point, you can go to the repo and download the code, and it's available if you want to use it. The code up there is compatible with the 1808 release. We are actively at work trying to make it compatible with the 18.11 release. And we are always constantly in this catch-up mode where we're trying to catch up with an upcoming DPDK release. And all of that will be eliminated once we get into the mainline repo. Many of the core libraries for networking are available on Windows. I know DPDK has added support for other hardware now. I know the Quick Assist technology hardware from Intel has PMD now. We're going to be looking at that next, and there's no timeline as to when we're going to use that, but we have some other projects inside Intel where we think we can make use of that. And we are seeing a lot of interest from players. You saw the previous presentation where Cisco was talking about downloading this code and using it in a video media processing industry where these media players need fast packet processing. The other thing I thought was, I talked to Jeremy a bit just before this, it might be great to add this into the UNH test bed, where we can have a Windows system there with some NICs in there where we have support. And if every patch that goes in tests it on Windows, that would be a great thing. So from a 10,000-foot view, if you look at the architecture for DPDK, it is very similar to what is on all other OSs. There's the application DPDK and the PMD in the user space with a little UIO component. On Windows, we actually had to write this UIO driver, and it's a pretty dumb interface kind of thing. All it does is just get you access to the networking hardware into user space. And in Windows, there's one other thing, though. It has to allocate physically contiguous memory, because in the Windows operating system, user space cannot allocate physically contiguous memory. It has to be done in kernel, unless you know of a backdoor way to do it, Omar. We don't know of another way to do it. So that's what the UIO driver would do. And the source is available up there, but it does have some problems. And some of the problems were the UIO driver would take over the entire network port. So if you had a dual port 40 gig Intel adapter or something, and you bound the UIO driver on one of those ports, that's it. Nobody else could use that port. It was dead to the kernel wouldn't see it because it was completely taken over by the UIO driver. And of course, that doesn't work in a scenario where you have live migration. So that was one problem. Second, it's not multi-user, multi-process secure. So any two DPDK processors using the same UIO driver could potentially overwrite each other, and that was another problem. The network device could not be shared with the kernel driver, like I said. Once UIO driver was bound to that port, that's it. It took it over, and only the DPDK applications on top would be able to use it. And then the fourth bullet point is a very critical point on Windows. On Windows, you cannot have a kernel module or a kernel driver that is not signed load. Windows will not load an unsigned driver in kernel. So think about a consumer of DPDK. Now you're writing an app, you have some sort of an app that you want to use with DPDK, you download the source, you can build this UIO driver, but you can never deploy this because you cannot get it signed. So on the side, we are talking with Microsoft, we are thinking of finding some ways where we can, users can submit this driver from sort of digital signing or some certification or something of that sort. But that's still not an ideal way. If somebody comes up with a new device with a pole mode driver, they have to add an INF to change into that UIO driver's INF. They have to add the device ID. That has to be resubmitted to Microsoft for certification. So it's not a very clean model of working. So certification is a big deal on Windows. So what we need is a solution that allows us to fix all of the other issues you see on the top. It needs to be shared with the kernel driver and things like that. So what we're proposing is a small change to the architecture. So it's not that small, but it's quite not insignificant, I should say. So on the left side of this picture, you'll see the applications on the top and the TCP/IP and the NDIS stack. NDIS is the networking subsystem in Windows, network device interface. Something specification?
Close enough.
Something like that. I've been working with it for a while. I don't know what it stands for. Kind of like the KNI in the Linux kernel. So on the left side, you see the network device NDIS stack, the normal kernel stack that you have in Windows with TCP/IP and all sort of protocol processing. On the right side is our DPDK stack. What we have done is we have added a new module here called the Secure API. Now, Omar and I were struggling to come up with a good name for it, so we were calling it a Secure API. Let's put that on there. That name is not final. We'll call it something else later. So essentially, it's like a secure API provider. It gives you access to the kernel layer to get access to your hardware, but also it compartmentalizes all of the resources that a user mode process is asking for. So by doing that, what you've done is you've isolated the DPDK stack away from the kernel networking stack, and separate DPDK multi-user, multi-process applications are also isolated from each other. The driver that you see there is the existing kernel Ethernet driver that's available on Windows. All network device manufacturers, IHVs on Windows, provide some sort of a kernel driver, and we are proposing a small change or API change, something to facilitate this process into the kernel device driver. And if you see right at the bottom, you can see there's one NIC where your compartmentalized and allocated separate resources for the kernel stack. I tried to use some sort of color coding. I don't know if it shows up on the big screen. But if you can see that the dark blue line from the secure API down to the proxy is a resource configuration and allocation path, whereas the red color path is the direct path to the PMD, to the NIC, to the filters. Now, how this secure API how does it look like and things like that? I think for that, I have one more slide before I hand it to you, Omar, sorry. So what are the benefits of this? I just spoke about it a little. So of course, the memory resource allocation can be done in the kernel. It can be separated off and isolated for each process and separate from the kernel stack that the kernel is using. The security is enforced because you can use a PASID or something of that sort to actually encompass and isolate everything into one memory resource, queues and all that. You can filter specific flows the way you want it. And the kernel driver can be fully certified. That's a big deal, like I said in the previous slide, for Windows. The network drivers today, the kernel drivers, everybody has to undergo a thorough certification under Windows. They call it the WHQL, WHQL, Windows Hardware Qualification Certification. And if Microsoft or the WHQL team inside Microsoft, if they can add some more tests to make sure that this path is also tested and certified, that would be a great thing. And so every IHV can release their pole mode drivers along with the kernel driver, and everything can work in a DPDK stack. And of course, one big benefit is there's no UIO driver required. And with that, I'll hand it off to Omar to talk more.
Okay, so what do we mean by secure API? We intentionally left it vague. There's many ways to compose this secure API. But the way to think about it is, what is it that I need from this secure API? Now, at the very, very highest level, what we're trying to achieve here is, we're trying to say, okay, we need a security model that works both in Linux and Windows. There's no point in Windows going off and reinventing the wheel or designing something that is going to be different from what Linux has. So what we're looking for here is collaboration on the architecture direction for how to secure DPDK applications, okay? Okay, so at a high level, ideally the API is device agnostic, okay? Now, it should also be OS agnostic. After all, you're going to have a set of APIs inside of your OS, and ideally if those APIs are aligned as possible, that's just general goodness. It's goodness for us, as we don't have to keep reinventing things, and it's goodness for the IHVs and ultimately for the customer, because there isn't two different models to work off of, okay? Now, device agnostic may be a challenge, as I'll get into more details in later slides, specifically because for DPDK, you could have NICs that span the whole gamut of very simple, basic, bare bones IoT devices, all the way to your super server NIC with all the bells and whistles and super advanced offloads. So how do you come up with an API that's somewhat generic for that? Ultimately, what we want to achieve is we want to put every single application in its own little sandbox, where that application is constrained and limited in the amount of resources that you can consume. So both from, think of it as a resource consumption or mitigating a DOS vector in terms of resource consumption point of view, and also performance isolation, okay? So why do we do this? So today, when you use DPDK, you're effectively trusting the entire machine and that physical NIC, as Ranjit mentioned earlier. And in some ways, if you didn't apply any security or policies to your top-of-rack switch, you're essentially exposing your entire fabric to that application. So essentially, you have to say, well, if I'm running DPDK on a native machine, I'm actually trusting that entire native machine. Ways to work around that? Well, great, you can put the machine inside of a virtual machine, but then in that case, you still have the same limitations. I could have one application that attacks another. So for example, if I have a case where I have a DPDK application, but then I have a very strict, proprietary, secure, third-party application, and the two can't coexist on the same OS, and that's kind of a problem in terms of DPDK interoperability, or just coexistence inside of that OS. If you move it into a virtual machine, then you'd have to have multiple virtual machines. So now you're using the fabric as your IPC mechanism, whereas you could have used the OS as your IPC mechanism. And if you're putting inside of a virtual machine, you're pretty much trusting whatever securities you could put around that virtual NIC, be it a synthetic virtual device or a virtual function. Meaning that in the prior example, in the physical machine scope, you have to apply some sort of security to your top-of-rack switch to make sure that you're not contaminating the fabric. Well, in this case, because you've allocated a synthetic NIC or even a virtual function to that VM, you have to try to implement the same. Now, ultimately, this is where we want this to be. We want to treat a DPDK application just like any application. I'm able to limit what he can consume, and I'm able to control how much and what he talks. And obviously, multi-instance. So going a little bit deeper into the model, a couple of things stand out. So ideally, we're able to limit the amount of memory that that application consumes. Ideally, that application is based off of virtual addressing, and it uses the device's MMU for any translations. So for example, think of a memory registration model, a la the RDMA model. Now, we understand that not all devices are going to support this, and not all devices will have MMUs. The second part, ideally, is a hardware-agnostic kernel space controlled path visibility. Again, this becomes a challenge if I have very, very simple NICs and server NICs. So an API that encompasses the entire gamut needs to be developed and thought through. For example, if we assume a server NIC, we can say, okay, I can limit this DPDK application to only consume, say, 10 Q pairs or 2 Q pairs. Whereas this other application could consume, 1 or 100. It could be sliced and diced many different ways. And then obviously, as I mentioned, the per user, per resource caps reservations. There's another aspect to this that I'll get into later slides, because in this, what we're describing here is essentially how do I secure an application within the machine scope. But ultimately, there's the physical machine and the virtual machine scope. So later on, I'll describe how we secure a given virtual machine within a physical machine. Now, one sticking point that really stands out with the DPDK model, especially when we think about availability, serviceability, diagnosability, is just general operationalization. For us at Microsoft specifically, when we run any applications in the cloud or even on-prem, we have to make sure that that is actually diagnosable and serviceable. So you have a wide gamut in the engineering spectrum. You can go all-out performance and sacrifice some security diagnosability, or you can have some diagnosability and start to cut back on the performance. We're trying to strike a happy medium between the two. And it should be possible. I mean, it's done in the RDMA space. It should be possible in DPDK space also. So by operationalization, I mean the ability to monitor, diagnose, and see what an application is doing. For example, if I have a native machine, and that machine is trusted and dedicated to DPDK, and there's other applications running on there, I can't do very much from an OS point of view to assist in diagnosing and making sure that the application is running correctly. However, if I'm able to provide a mechanism, like the one we're trying to achieve here, where I can constrain an application as to what he can do, then I can more easily operationalize, meaning that if an application running DPDK is misbehaving, I don't have to worry about another application being a victim of that. So now we'll talk about multi-tenancy. So today, if I use DPDK, I'm basically allocating an entire NIC to it. That's kind of a problem, because then I have to allocate another NIC for my host to even communicate, or my machine to even communicate. That's multiple ports, multiple cables. It has a cost. It also has a cost in terms of IP management. Now, in the prior presentation, we talked about how we're putting direct device assignment for the NICs inside of a VM. So it's the path to enable the ease of use of VMs with DPDK applications on Windows. And the first step to that really is just allocate the entire NIC to the VM. The VM consumes the entire NIC, but obviously that doesn't address the security problems that I've mentioned. Now, ultimately, this is where we want to be. We want to have a VM that's able to run DPDK applications, and it's not just a dedicated VM for DPDK. It's DPDK as multiple instances protected from each other within that virtual machine. And to do that, you have to have, at least in the Windows world, a synthetic data path and a hardware accelerated data path. And I'll describe in later slides why this is the case. Now, if I give a virtual function to a virtual machine, then I'm getting great performance. But in a way, I'm bypassing security, right? I don't have a synthetic mechanism or host-mediated I/O to actually sanitize that traffic, because the virtual function, by definition, is bypassing the host. It's talking directly to the NIC. So how do we secure that? Well, for one, we have to control what gets placed on the fabric. Okay? We have an engine in Microsoft called GFT, generic flow tables. It's basically an offload of another technology called VFP, virtual filtering platform. And what this does is it transposes and secures the traffic. So it basically parses all the traffic that's coming in, that's coming out of a VM and going into the VM. And you're basically doing NCAPs, DCAPs, VXLAN, MBGRE, IP and IP, MAC and MAC, any modifications, multiple nesting, it's just the whole gamut of things. That can be offloaded to hardware. So when you have a virtual function in place, you can use GFT as a mechanism to secure the traffic going in and out of the VM in terms of what is contained in that traffic. The second part of that is being able to control the VF's attack surface to the NIC's VEB, right? So you don't want the case where the NIC is spraying traffic on, say, traffic class 5, for example, like crazy, to the point where he's confusing the VEB and affecting other VFs on the same VEB. So in this case, you would use something like tenant DCP to do auto configuration and sanitization at the 802.1p or even IP DSCP level for that traffic that's coming out of the VF. The second part to securing tenants is really controlling how much they place on the fabric. So again, these are QoS policies applied on a per VF basis in terms of rate limiting the bandwidth for egress, reservations for egress, and caps for ingress. We'd love to do caps, we'd love to do reservations for ingress, but that's a pretty tough problem to solve. And lastly, number 3 is a variation of the same thing that I mentioned earlier. If I'm within a machine scope and I'm able to control the amount of resources and rate of resource consumption on behalf of an application, when you translate that into a multi-tenant world where I'm running a VM on a host, I need to be able to do the same thing from the host on behalf of the VMs. So I need to be able to restrict and rate limit the resources consumed by a given virtual function on behalf of a VM. Now, there's a twist here. And Windows virtual networking is slightly different from Linux virtual networking, although that's expected to normalize at some point. In that in Windows networking, when you have a synthetic device, a virtual function is a dynamic acceleration. So you basically allocate a VM, and when you allocate your synthetic device can expose DPDK functionality, and then you dynamically add the virtual function with really no disruption to the consuming application. Of course, there's a difference in performance, right? Of course, if you're going through a host-mediated, kernel-mediated I/O mechanism, you're burning cores, and it's not going to be as performant or as good of latency as having a near-native data path like the virtual functions. So once you bring the virtual function online, now we're able to accelerate the applications with near-native performance. And the virtual function can be dynamically removed also. So why would we do this? Well, the clear cases here are live migration. If I have a VM that I need to live migrate to a different host, then I need to preserve the live part of live migration. If I remove the virtual function, I need to keep the data path active in some way. Of course, it would be in a degraded mode here relative to the performance that I can get from DPDK. The second part here is general operationalization. So let's say that I have a virtual function driver that is bad. It has a bug. We discovered some case where I deployed this virtual function driver. It was running for 3 months, but there's this one rare case where it just blows up with this given traffic pattern. Well, I need to be able to dynamically remove and mitigate. So we can take a performance hit in terms of our data path, but we avoid the crash situation and outage to the customer. And then lastly, general updates. If I have a device that I've allocated to the VM, or even at the host at that, I need to be able to update that device. I mean, device drivers come out, they have fixes. So when you update the device, you have to remove it from the guest, essentially update the driver and reinsert the virtual function back. And those are the 3 primary models that we use for having a synthetic data path with VFs treated purely as accelerations. Now, there's other areas of investigation that we're looking at. We find AFXDP to be super interesting. It seems to me, at least from my survey of the community, that the Linux folks and DPDK folks are somewhat aligned on simplifying the data path and leaving all control up to the kernel for device management. eBPF seems very interesting to us. We like the technology. At least the items that I described earlier in terms of what GFT is could be composed of constructs from eBPF. Our GFT model is somewhat coarse. eBPF is more granular. Therefore, you can construct GFT from eBPF. And lastly, we know that there's work going on for VFIO. Specifically, this requires virtual IMMU work. That is at a much more advanced stage in Linux than it is in Windows. And at least from a networking point of view, we don't have anything on the roadmap for really looking at virtual IMMUs. I do know that within Microsoft, there is interest from the graphics folks to consume this. Maybe at some point that accrues over. Now, before I end the slide and the talk, there's many ways to slice and dice and implement a secure API. The user space hardware acceleration problem, I consider that a solved problem. I think it was solved by InfiniBand over a decade ago. It's very high performant, and it provides per resource, per user isolation. Today, we know that there are solutions that can be built this way. So for example, in Windows, you could use Network Direct v2, which is essentially the Windows user space RDMA surface. And you could code your PMD up to this, and if you have the appropriate level of granularity in your filters, then you're able to provide DPDK functionality with user space access, with kernel-mediated resource constraints, QoS caps, and all the bells and whistles. That's available today. But obviously, if you wrote a PMD to that model, it's not a model you can easily translate over to Linux, unless you wrote your PMD on top of verbs. If you write your PMD on top of verbs, yes, design pattern-wise, it's the same thing. Unfortunately, the constructs are pretty different. That's complexity for the IHVs. I mean, they're effectively designing the wheel twice. But it's there now, so it can be consumed now. So if a solution was needed right now, that's the vehicle that's there. Ultimately, are there other ways to do this? Potentially. That's where AFXDP comes into the picture. And that's where additional work around flexible IOV, using passids as the mechanism to do the mapping and constrainment, becomes interesting. Which one of these ultimately will win out? We don't know. That's what this presentation is about. This presentation is about us trying to reach some consensus with the DPDK community and the Linux community to simplify the work for the IHVs and ideally result in a better quality of product for the customers, regardless of what platform they're running on. So we'd love you guys' feedback on this.
Yeah, so this was our last slide, and as you can see, you can contribute to the draft repo, just reference that in the contribution. That's how Cisco, as they mentioned in the previous presentation, they found the code and they started downloading from their users, and they've actually submitted patches back to us. So help us make it better. And I think that's it. Yep.
We're happy to take questions.
Any questions?
Okay, so in your previous slide, there's a layer called GFT that enforces all the checking on the rules, like make sure that VM can only send the traffic that belongs to it, right? So where do you think the GFT would be living? Would be in the NIC? Like, would you be using a smart NIC, or would be in the driver? Like, which place do you think is the best?
So if you do it in a device driver, then you're assuming software-mediated I/O. So in that case, then you're eating away at the performance benefits of using a hardware data path. Now, there's many ways to implement the GFT model. It's no secret that in Azure, this is implemented through an FPGA. It's called ExcelNet. In private cloud proper, we don't really use FPGAs. So we expect that functionality to be implemented in the NIC. And for the IHVs here, we have been talking to them over the past few years about how this technology is implemented, and there are specs out for how to implement it. My understanding is that most of them are working towards this. No solution yet exists for private cloud on Windows for this. Similar solutions do exist on Linux, though, using the same technology.
Okay, so if you implement that in, let's say, in a smart NIC, I would guess there will be hardware limitation on the number of, let's say, flows that you can classify. Let's say if you run like 100 containers, and each container will presumably have different TCP IP ports, and you will be classifying on, let's say, 5 tuple. And then would that be a sort of constraint on this model?
Is your question around how much density is required
How much,
in terms of flows?
Like, how many flows can you classify if you put this thing in the hardware?
It comes down to how the hardware is designed.
Okay.
I mean, if you have a device where you're offloading rules per se in the eBPF-like model, then it's probably going to be more scalable. If you have a model where you're doing state tracking on all of those flows in some exotic way, then it's going to cost more hardware resources, and you'll be constrained in the amount of density that you can apply to that. It really comes down to hardware design. From our point of view, we expect hundreds of thousands of flows.
Okay. Thank you.
Was part of your question, do we have to have a smart NIC to do this? Was that your question? Was that part of the question?
Is it the desired model, or would you rather place it in the driver?
It could be either. Yeah, you can implement this in the driver too. So.
Okay. Thank you.
Sure.
I wanted to ask a bit about the management of this. So you mentioned the resources and the multi-tenancy and all this. So how do you plan to manage all this? So who does the management? What is the management interface? How do you allocate resources to one virtual machine? And
yes, so that's the orchestration part. And if you look at the example for how the resources are managed on a host on behalf of the VMs, on the host, you're going to limit the number of queue pairs, the number of CQs, the amount of memory, all of these properties of what a virtual function is. You're going to control that from a host point of view, because you don't want any given VM being able to DOS its peers. That same model then applies when you go inside of the machine. Now, I'm on a machine instance. I have a kernel, I have user space, DPDK is in user space. I have the same pattern of a problem. I have many applications, and I shouldn't have one application draining all of the queue pairs or all of the map memory space on behalf of that NIC to the point where he drowns out the other applications. So some configuration is needed. On a host, that's basically the cloud admins orchestrating what those properties are and what the settings are. And you use templates to apply those. Once you get into a VM, and now you're having acceleration at the application level, then yes, some orchestration mechanism is needed inside of that machine to apply all of those policies.
I was just asking if what is the entity that will implement and expose, and what are the APIs? If you thought about what are the APIs that will expose for management, and so you need some kind of
Yes.
central entity
So-
on the host, because you have to have some remote. You don't want to go each machine and type what resources goes where. So it needs to be somewhere centrally managed. So did you think about all this?
Yes. At scale, that would be applied through profiles, right? And like I mentioned earlier in the talk when I mentioned the ND model, the orchestration mechanisms for applying all those caps in an RDMA specific point of view already exist, right? You can already apply all these policies. But the goal here is not to make it a device specific policy application. It should be abstracted away from the device so it's not, so it's generic basically. I should just be able to go to Windows, run some generic hardware agnostic commands to apply what those caps are locally or remotely, and the same thing in Linux.
Thanks.
Okay. Thank you, guys.
Thank you.